Newton's first law expresses the principle of inertia. The natural behavior of a body is to move in a straight line at constant speed. A body's motion preserves the status quo, but external forces can perturb this second law. The change of motion of an object is proportional to the force impressed, and is made in the direction of the straight line in which the force is impressed. By motion, Newton meant the quantity now called momentum, which depends upon the amount of matter contained in a body, the speed at which that body is moving, and the direction in which it is moving. In modern notation, the momentum of a body is the product of its mass and its velocity, where all three quantities can change over time. In common cases, the mass does not change with time, and the derivative acts only upon the velocity. Then force equals the product of the mass and the time derivative of the velocity, which is the acceleration, as the acceleration is the second derivative of position with respect to time, Newton's second law. In modern form, states that the time derivative of the momentum is the force. When applied to systems of variable mass, the equation above is valid only for a fixed set of particles. Applying the derivative as in can lead to incorrect results. For example, the momentum of a water jet system must include the momentum of the ejected water. A free body diagram for a block on an inclined plane illustrating the normal force perpendicular to the plane, N, the downward force of gravity, mg, and a force F along the direction of the plane that could be applied. For example, by friction or a string, the forces acting on a body add as vectors, and so the total force on a body depends upon both the magnitudes and the directions of the individual forces. When the net force on a body is equal to zero, then by Newton's second law, the body does not accelerate, and it is said to be in mechanical equilibrium. A state of mechanical equilibrium is stable if, when the position of the body is changed slightly, the body remains near that equilibrium. Otherwise, the equilibrium is unstable. A common visual representation of forces acting in concert is the free body diagram, which schematically portrays a body of interest and the forces applied to it by outside influences. For example, a free body diagram of a block sitting upon an inclined plane can illustrate the combination of gravitational force, normal force, friction, and string tension.